Good afternoon. My name is Diane Harrison. In my capacity as the president of California State University, Monterey Bay, I want to welcome you for making this historical appointment, as we have the opportunity to welcome one of the most notable figures in the 20th century, Dr. James Lovelock. Welcoming Dr. Lovelock here today is an opportunity that we do not take lightly, as we are at a stage in our development as a university where we look back at the last decade and ask whether or not our academic design is visible, viable, and especially for training and educating students for the 21st century. What we are finding is that our pursuit of excellence and our quest to develop a culture of innovation parallels the life of Dr. Lovelock, inasmuch as our non-traditional ways are under constant scrutiny by our publics. Yet, like Dr. Lovelock, we persevere in our search for solutions for improving the quality of knowledge, our search for the truth, and for transforming the values of our students to lead socially responsible lives. Moreover, we not only remain aware of the fact that we must demonstrate ourselves to be an efficient and accountable university, but we must also stay the course and remain true to the overall conceptual, interdisciplinary, intellectual design and utilize new and varied instructional approaches, including bringing world-class scientists such as Dr. James Lovelock to CSUMB. In this light, let me add that Dr. Lovelock is one of the most eminent scientists to visit any CSU campus in the history of our university system. For this reason, we are honored to have him here with us today, and we appreciate your coming to hear Dr. Lovelock. Dr. Lovelock, we are truly honored that you have accepted our invitation and have joined us here today, and we welcome you and your wife to the United States and to California State University, Monterey Bay. Oh. In keeping with our vision statement to remain collaborative in our orientation, we have actively sought to bridge between the town and the gown and want to especially welcome members of our surrounding community to your university. We want to thank you. Yes, it is your university. We want to welcome members of the media, including our student newspaper, as well as regional newspapers, the KRXA and KAZU radio stations, AMP, the local community access channel, which will be running this lecture several times a day for the next few weeks. Instructional technologies for providing closed captioning, and also streaming for the first time one of Dr. Lovelock's lectures over the internet. You may also be interested in listening to Dr. Lovelock's interview that will be aired by National Public Radio tomorrow morning. Special thanks to the College of Arts, Humanities, and Social Sciences and to Dean Renee Curry and her staff for their ongoing support. We'd also like to thank the Big Sur Environmental Institute for bringing Dr. Lovelock to our region and for partnering with us today. I would now like to introduce a founding faculty member and professor who, without his efforts, this lecture would not have been possible. Someone who contributes to the fields of both social ecology and ecological psychology, Dr. Armando Arias.
Okay, let's get this show on the road. As one of the founders of CSU Monterey Bay, I reflect on the earliest times of the university, even before we hired the first 14 faculty members. I remember how we began to envision a university whose majors would be truly interdisciplinary by design. My thoughts were drawn to the first time I met Dr. Lovelock at the Western Behavioral Sciences Institute, founded by the great psychologist Carl Rogers. I was struck by Dr. Lovelock's notion of interdisciplinary thinking, or a type of thinking that is distinguished by its ability to invite student inquiry for the discovery of big ideas and that link several areas of knowledge. My sense is that you too will be struck by Dr. Lovelock's lecture today. Not only by how he interconnects ideas, but also what a profound commitment he has to the analysis of human condition and the fate of humanity. Still vigorous at 87, almost 88, Jim Lovelock is a towering figure in environmental science. You may be interested to know that Dr. Lovelock invented the electron capture detector, which allowed the first trace detection of pesticides such as DDT and PCBs, and provided the scientific basis for Rachel Carson's phenomenal book, Silent Spring. He discovered the ubiquitous presence of CFCs, which are chlorofluorocarbons, in the atmosphere that triggered the discovery of their disastrous role in the ozone depletion by Nobel Prize winners Rowland and Molina. His work at the Jet Propulsion Lab for NASA on the Martian atmosphere led him to reflect on life on Earth and develop the Gaia hypothesis. He was basically the person that they went to ask him, is there or isn't there life on Mars? He told the government, no, there isn't, but just recently he told me secretly, I think there is. There are few people, if any, who have had a greater influence on our environment and on the nature of the Earth as a whole. Now known academically as Earth system science, this holistic view elucidates the many complex feedback loops between life and its environment and change forever the way we think about our biosphere. Dr. Lovelock, I'd like for you to know that this university has a division of science and environmental policy, and students earn a degree in Earth System Sciences, a term you coined. Dr. Lovelock received PhDs in medicine, biophysics, and is the author of over 200 scientific papers on medicine, biology, instrument science, and geophysiology. He's an independent scientist of extraordinary scientific breadth and a prolific inventor and author. He works out of a barn-turned-lab in Cornwall, England. For his work, he has received 9 honorary doctorate degrees and numerous scientific awards. During his career, Dr. Lovelock was awarded the Rockefeller Traveling Fellowship in Medicine and served it at Harvard University and the Medical School in Boston. He has also become a professor of chemistry at Baylor University of Medicine in Houston, Texas. He collaborated with those at the Jet Propulsion Lab on lunar and planetary research. He was elected a Fellow of the Royal Society. He was awarded the Norbert Gubier Prize of the World Meteorological Organization and the first Amsterdam Prize for the Environment by the Royal Netherlands Academy of Arts and Sciences. He received both the Nonino Prize, the Volvo Environmental Prize, as well as Japan's Blue Planet Prize. Let me catch my breath. 10 more pages to go, but I'll summarize that in one sentence. He is the originator of the Gaia hypothesis that you're going to hear all about today, now known as Gaia theory. And he has written 6 books on this subject. Dr. Lovelock offers a compassionate as well as a passionate view of the relationship between science and society, and is one of the most outstanding and creative thinkers of the 20th century, and for that matter, the 21st century. Lovelock is among the most important contributors to the scientific thought in the last 100 years. His work has led to the founding of the Green Movement, and his famous Gaia theory has changed the way we view the Earth. Dr. Lovelock's recently published book, the one that will be in the foyer after the lecture today for book signing, is The Revenge of Gaia, and it was written as a wake-up call and is based on a top-down view of the Earth. His talk today will be about the climate change now expected, seen in the context of an Earth system that self-regulates with the goal of keeping its temperature and chemical composition always favorable for life. And for Pete's sake, it's done a pretty good job for the last 3.5 billion years. He sees the Earth as a physiological system and something that actively responds to change and is quite different from the dead planets, such as Mars and Venus, that respond passively. Dr. Lovelock is currently the president of the Marine Biological Association, and he's an honorary fellow at Green College, Oxford University. He's an independent scientist. He's an inventor. He's an author. He is the father of the green movement. I give you Dr. James Lovelock.
Thank you, President Harrison, and thank you, Armando, for that wonderful introduction. I feel you've already given me my lecture for me. Maybe I can go home now. But those of you who've seen the poster advertising this particular lecture will get the impression from the portrait of me there that I'm a pretty cheerful person. And my wife, who's sitting in the front row, Sandy, will confirm it. So a lot of you may wonder, why on earth should I write so gloomy a book as The Revenge of Gaia? It's a book that predicts a grim future for civilization and warns of grave dangers for us all. Well, I did it as a result of a wake-up I had about 2 years ago. Up until then, I think most scientists, they knew about global warming, but somehow it was an academic subject, not something that was going to affect our lives all that much, apart from getting pleasantly warmer. 2 years ago, Sandy and I received an invitation to go to the UK's primary climate research centre, I think a place called the Hadley Centre at Exeter in Devon, and conveniently it was only about 40 miles from home. Now, they really did us proud when we got there. We went to all the departments in the centre and saw all of the scientists that were working on climate change problems. For example, we went to, first of all, to people who were concerned with the melting of the floating ice at the North Pole. And any of you who've read Al Gore's book will know that, or seen the film, will know how important it is that that ice, if things go on as they are, will all be melted in about 20 or 30 years. You'll be able to take a sailboat to the North Pole, and an enormous amount more heat will be absorbed by the Earth as the sun shines on dark seas, not white reflecting snow. And then we moved on to others who were working on the melting of the glaciers around the world, and they warned of how as it warms, their rate of melting would get faster and faster. And then we saw some other scientists whose concern was the tropical forests and the way that, in a sense, they were also melting, vanishing as the world grew warmer. Then we moved on to another department where we heard about the dangers to the boreal forests, that's to say the great conifer forests of Canada and the northern USA, and also, of course, of Siberia, going right the way across the north of the world. Now, as the world warms up already, those forests are under great threat from forest fires and so on, and also they're responding to heat by moving their position, moving further north. Finally, we ourselves brought a message about the way that the great oceans of the world, that are 70% of the Earth's surface, people tend to forget that, and the way that as they warm, they become less and less a habitat for algae, which are the primary producers, and for life generally. But I'll be talking more about that later. Now, each of these groups of scientists and ourselves talked about the tipping points, if you like to call it, for all of those separate systems, and they were all very close to them or had already passed them. Yet still, everyone talked about the problem separately and academically, almost as if they were talking about another planet like Mars, not the Earth. And this was worrying enough. But perhaps the thing that was gloomiest of all was the way that each of the groups looked at their own problems separately. They knew about the others. For example, the people studying the melting ice knew about the vanishing forests, but they didn't somehow factor it in and see global heating as a complete planet-wide phenomenon. And of course, having started and gone there 40 years ago with Gaia as first a hypothesis and then a theory, I naturally had a top-down view and saw the whole thing as a planetary entity, and in those circumstances the combination of all their stories was particularly gloomy. And it was that after we talked about it driving home from Exeter, that made me decide to write the book The Revenge of Gaia. Now, when I started to write my book, I wanted to make sure that it was scientifically accurate and I wasn't carried away by my own fears. So I read the Intergovernmental Panel on Climate Change's report. This was a great big volume published in 2001, and an update is due next year, I believe. Now, it's a story about global warming told by scientists from all around the world. I would guess that getting on towards 1,000 of them have contributed. And it's written in good, clear language. I recommend that any of you read it. But it's written with the usual detachment of scientists, and in no way really as any kind of doom story. Yet, when you take some of the predictions of it, they are amongst the scariest things I've ever read. Indeed, I think it's the scariest official document that I've ever read. Now, all that my book does is to present the untold consequences of this report in a way that's intended to be comprehensible to non-scientist readers as well as scientists. And I've written strongly to make it, as you heard, a wake-up call. It was all too clear that the message from the climate scientists was not reaching the public, and especially not here in the USA. My book takes an apocalyptic view of the future because I see 6 to 8 billion of humans faced with ever-diminishing supplies of food and water in an increasingly intolerable climate. Now, to sort of illustrate what I'm saying here, I have on the first diagram on the picture 3 models of the Earth when it was in an ice age, as it was 14,000 years ago, as it is now, and I'll come to what it will be in perhaps by the end of this century, a hot world, 5 degrees warmer Celsius than it now is. Now, I think you will see dark colors and gray colors mean lots of life. White means none. In the Ice Age world, of course, the great polar regions were much extended. The glaciers went down as far as St. Louis in the United States and as far as the Alps in Europe. And the southern polar ice cap was also somewhat extended. But apart from them, there's life in the rest of the world, apart from the main oceans in the tropics, where the water was too warm for abundant algal life. You'll also note the continents were much bigger. Lots of land that's now below water was above the sea. Indeed, the sea level was 420 feet lower than it is now. If there had been a civilization around on the edge of one of those continents, just imagine what would have happened when the sea level rose that much. It would really be deep and under. Now, as one point about this is it emphasizes what I've always thought, namely that the great system of the Earth, which I call Gaia, likes it cold. It prefers it cold to hot. And in a way, Proof of that is the fact that during that ice age cold, the carbon dioxide in the atmosphere was pumped right down to 180 parts per million, and it takes a lot of life to do that. And now we come to our world as it is now, and as you can see, the ice caps, well, have retreated way back, but the ocean life is now driven up much closer to the poles than it was in the ice age. And the land surfaces have much more in the way of scrub and desert and much less in the way of lush vegetation. And so even before we started polluting, the CO2 level had gone up to 280 parts per million. I will try and move the diagram up. If there's anybody standing here can help me with that, I'm not quite familiar with this computer, I'd welcome it. Is that doing it? Yeah.
You continue to speak.
Okay. Well, thank you. Now the hot world, something perhaps 100 years from now, is beginning to, it was. No, it's not going to vanish altogether. No. Oh, there we are. That's fine. It has come into view, and thank you. Now we've gone too far, but never mind. I think you can see that the areas of scrub and desert and uninhabitable regions have now extended widely, and the only part of the world that is really habitable is the North Polar regions. And there will be oases, of course, on the great continents, and there'll be islands where the climate is not so severe that people will continue and life will continue. But believe me, if that happens, it's going to be a very grim world indeed. Now, you may well ask at this point, why have we scientists let this potentially disastrous future steal up on us unawares? Well, there are several reasons, I think, and among them was our success at solving the important but much more manageable problem of stratospheric ozone depletion. I suspect that gave us false confidence in our ability to deal with what is a far greater danger, the accumulation of carbon dioxide. Another reason for the slow recognition of the threat of adverse climate change is the division of science into almost unconnected specialties. At the last count I made, there were at least 30 different branches of biology alone, and the same is true of chemistry and physics. And if you look back at the writings of the earth scientists 40 years ago, you will find them confident that the composition and climate of our planet could be completely explained by chemistry and physics, and that life was just a passenger. At the same time, if you look back at the writings of life scientists of that period, you will find them confident that organisms just evolved according to Darwin's great vision and adapted to an Earth that was described by their earth science colleagues in the building across the campus. They hardly ever talked to one another. Now, this was a harmful and irrational division of science, and it's slowly fading away, but it still persists and prevents us from seeing the Earth itself as a planet almost as different from Mars and Venus as is one of us from a stone statue. 40 years ago, I was working at the JPL, not so far away from here, and was given a wonderful opportunity to see at first hand evidence about the true nature of Mars and Venus. In spite of what Armando said, I saw them as quite obviously dead planets, and still do, and quite different from our lush and lively world. They seem so different that I introduced the hypothesis that life at the surface regulates the composition and chemistry of our Earth so as to keep it habitable. My friend, in the village where I lived in England, was the Nobel Prize-winning novelist William Golding, you know, Lord of the Flies and all that. He suggested, when I told him about it, that I call the hypothesis Gaia, because he said that any sort of big thing about the Earth needs a proper name. I was welcomed it. Who would refuse an offer from such an eminent author? Not only that, it was a 4-letter word. A lot better than Earth system science or something like that. Later, during the 1970s, I developed the idea further in collaboration with the eminent biologist Lynn Margulis, who was introduced to me the notion that the really important part of life in the regulation were the microorganisms, the algae in the ocean and the bacteria in the soil. We large things are kind of recently Johnny-come-latelys and not so important. But we soon found that our hypothesis was very unpopular. Biologists in particular were almost enraged about it, and in the 1970s they trashed the infant hypothesis in the mistaken belief that it was, like creationism or intelligent design, contrary to Darwin's great vision. Their demolition was so effective that even today an awful lot of scientists are still unhappy with the word Gaia and see it as some kind of New Age fantasy, not science. Actually, I don't think it matters all that much what you call it, but I'm going to go on calling it Gaia in spite of the trouble it causes. Anyway, I went on to refute the biologist's criticism with a numerical model called Daisy World, and this led to, together with 10 predictions that have been either proven or are still under test, to what I call Gaia theory, and is also called Earth system science. It's a top-down view, a physiologist view of the Earth system, and sees the Earth as a dynamic, responsive planet, and explains why it's so different from Mars and Venus. Now, in different times, earlier days, these quarrels would have just been part of the natural history of science. It usually takes 40 years for any theory to get established, and Gaia's just about on course. It's now 41 years since it was first thought of. But unfortunately, the quarrels now seriously interfere with the evolution of a proper understanding of the Earth system at a time when we truly badly need it. We need it to understand the consequences of adding greenhouse gases to the air, and the consequences, equally importantly, of removing natural ecosystems, forests, for farmland. Each of these acts disables the Earth system's capacity to regulate itself. And unfortunately, most of the large climate models that are made around the world still rely mainly on atmospheric physics alone. Even the influence of the clouds and the ocean are incompletely included, and the effect of the Earth's ecosystems is included hardly at all. It isn't that they're not trying, it's just a very difficult problem to include all of these things in such complex models as those that predict future climates. And it's a pity we didn't start doing it 20 years ago. So we're left in a position where present-day climate models are good at explaining past climates, but may be unable to predict the course of global heating. In 2001, there was a serious attempt to bring Earth and life science together. At a major scientific meeting in Amsterdam in the Netherlands, over 1,000 Earth and life scientists signed a joint declaration that had as its first point, the Earth system is a self-regulating system comprising all life, including humans, the atmosphere, the oceans, and the surface rocks. My friends who were at this meeting wrote to tell me that Gaia was now endorsed in science. But when I read the statement, I saw it as seriously incomplete. They failed to state that the goal of self-regulation is to keep the Earth habitable. Now, as any engineer will tell you, self-regulation is impossible unless you have a goal. Just imagine an autopilot that didn't know where to go. But to many biologists, the word goal still implies purpose and therefore teleology. It smacks of intelligent design and seems to require someone or something to set the goal. I think they're mistaken. In reality, to me at least, and I know there are many who disagree, goals are real and essential. Systems scientists and engineers know that goal seeking is a necessary property of self-regulating systems. Where we ourselves set the goals of our mechanical devices like autopilots and refrigerators, but living organisms, and that includes us, have their blood pressures and blood compositions and temperatures set by evolution and remembered genetically. So what or who sets the goals for Gaia? Numerical models of the Earth system like Daisy World and its much more complex descendants suggest that the goal of the Earth system was set by the specifications of the universe itself. The properties of the constituent atoms of carbon-based life have a very limited range of conditions in which they can exist. And it's this narrow range of physical and chemical states that sets the goal of Gaia. Natural selection, by its never-ending iteration, has ensured that organisms and the planet evolved to stay within those limits. A physical scientist or an engineer who was unfamiliar with biology might still think that a climate regulator that allowed ice ages and warm periods, to say nothing of the hot period that might soon be due, to be a regulator that was pretty poorly designed, quite a shoddy design. In fact, they would be wrong, because during the last 2 to 3 million years, the core surface region of the Earth, that's the region that lies between latitudes 45 north, that's about the latitude of St. Louis, and 45 south, I think that's about the latitude of Buenos Aires, includes 70% of the Earth's surface, and that big region has stayed comfortably habitable during both the ice ages and the interglacials like now. The temperature range of that region was about 5 degrees Celsius. Now, this isn't feeble regulation. It's just as good as is needed, and interestingly, is almost identical with the range of temperatures that we ourselves regulate at. We run normally at about 37 Celsius, but we can drop to 35 or rise to 40 and still be alive. So, in a sense, the Earth isn't doing much worse than we're doing. We think of an ice age as a diminished state, but this is just an illusion because we mostly live in the north temperate regions outside the core and don't like the idea of great glaciers coming down and sweeping the cities away. And as I've mentioned, there was more life on the Earth during the ice age. It's often stated in textbooks and by scientists who ought to know better that the Earth is just at the right distance from the Sun for life. Now, I think this is nonsense. Were it not for the regulation made possible by the presence of abundant life, the Earth would now be a hot, waterless desert with carbon dioxide as the main component of the atmosphere and a surface temperature well over 60 Celsius. And it would be a near interpolation between Mars and Venus. These facts are quite easy to calculate. You can almost do it on a single sheet of A4, and have been a touchstone that has sustained me during the long years of argument about the Earth. Just go. It's easy, I suppose, to see why scientists have been reluctant to abandon their familiar and comfortable paths, evolutionary biology has been a wonderfully rich and productive branch of science during the 20th century. But just as Newtonian physics was found incomplete at the particle and cosmic scales, so in a way Darwinism is incomplete when it tries to explain the world beyond a phenotype. In particular, it fails to see that evolving organisms do more than adapt to a dead and fixed world. They evolve and change in a world that was built by their ancestors. The air, the ocean, and the surface rocks are all either the direct products of life or else have been massively altered by living things, tight coupled with their environment. Self-regulation emerges from this evolution and is why, after 3.5 billion years and an increase of solar heat of 30%, we're still here. Now, I suppose I should get on now to how does my theory that I've just presented to you help with our current climate crisis? Well, in 1994, Professor Lee Kump, an earth scientist at Penn State University, and I made a simple model of the Earth that was intended to do no more than illustrate for the benefit of Lee's students just how our planet self-regulates. As time has passed, to our surprise, this model has unusually well predicted the course of global heating. Our model was of a simple world that had land masses and oceans in similar proportion to the Earth. We had plants growing on the land and algae growing in the oceans, and the model planet was illuminated by a star at the same distance and same luminosity as our Sun. The surface temperature of the planet depended on the greenhouse effect of the carbon dioxide in the atmosphere and the proportion of sunlight reflected by the surface and clouds. Carbon dioxide abundance was regulated by the growth of the planet's vegetation, both in the land and the sea, just as it is on the Earth. The most important part of the model was the variation of temperature of the area covered by algae or by plants. Now, in the laboratory, the growth rate of plants and algae both increase with temperature as it rises from 0 degrees Celsius to a peak, best growth at somewhere near 30, and then it falls away to 0 at 50 degrees Celsius. In the real world, it doesn't work quite like that. Geophysics intervenes. Algal growth and area cover, as you saw in the pictures before, increases with temperature from 0 degrees, as in the lab, but in the ocean, growth ceases when the surface temperature reaches 10 or 12, when the surface waters form a stable layer about 30 to 50 meters thick. When this happens, nutrients in the cooler waters below can no longer mix in with the top waters and the algae starve. And that, of course, is why the tropical oceans are so clear and blue. You can see right down through them. They're deserts. On the land, plant growth similarly increases with temperature until the rate of water evaporation becomes greater than the rainfall. And at this temperature, which is round about 22 Celsius, here also growth ceases, except in the special case of tropical rainforests, which have evolved a number of mechanisms to conserve water. Now I'll try and get on to my second slide. Whoever it was kind enough to help could go forward. Oh, good. How do I move on?
Just this one here. This one here, right?
Good. Thank you, Armando. Now, this is a run of this model I made with Lee Kump. And I'd like you to look at the top panel first. That shows temperature changes as we add carbon dioxide in the same way, more or less, as we are doing we start with a carbon dioxide level of 280 parts per million, which was the pre-industrial level, and then ramp it up steadily towards the levels we now have. Now, the upper line in the top panel is the temperature of a dead planet. Now, dead planets have lots of carbon dioxide, so just adding a little more wouldn't make the slightest difference. And they're very hot. As you can see, it's up over 60 Celsius. The small wobbles on the line are just changes in the orbital position of the Earth and the seasons as it moves around the sun. Now, those little wobbles are very handy because they're diagnostic. In the model, whenever the wobbles are amplified, the system is in positive feedback. And when they're diminished, it's in negative feedback. And I think you can see with the lower line, the kind of purpley color one in the top panel, as the CO2 is introduced, the line slowly ramps up in temperature, not an awful lot, but it starts fluctuating a lot more than the top line does, indicating an Earth system in positive feedback. And we strongly suspect this is the state we are in now. But suddenly, far down the tracks, when the CO2 reaches somewhere in the region of 450 to 500 parts per million, the temperature suddenly jumps and the Earth moves up to its hot, stable state. Indeed, there appear to be two stable climate states of the Earth, one around about the ice ages and now, and the other about 5 to 8 degrees Celsius hotter. And it's been in that stable state many times in the past. The reason for it was the decline of the algae from the oceans as they went, leaving the Earth to be regulated by land plants alone. Another thing to mention on the diagram is that you'll see the CO2 line suddenly diving down to pre-industrial levels. This was a kind of act of the modelers, or of God if you like, removing the CO2 suddenly and magically to back where it was. Now when that's done, it does very little to the temperature. You see things stay up where they were. Once you move up to the hot state, there's no easy return to the world we're in now. Now, what is modeled in this model is rather similar also to a geological accident that took place 55 million years ago at the beginning of what the geologists refer to as the Eocene period. In that event, between 1 and 2 million tons of carbon dioxide were released into the air. We are fairly sure about this quantity from measurements made by lots of scientists, in particular Professor Elderfield of Cambridge University. They measured the carbon and oxygen isotopes of sedimentary rocks of that time and confirmed that the quantity of carbon put into the air was the one I mentioned, and the extent of the temperature change. They found a temperature change of 8 degrees Celsius in the temperate and Arctic regions and 5 degrees Celsius in the tropics. And it took 200,000 years before things returned to normal. In the 20th century, we injected about half that much carbon dioxide, and if we continue business as usual, we will have released in 30 years from now more than 1 million tons of CO2. Moreover, the sun is hotter than it was 55 million years ago, but most important, we've disabled about 40% of Gaia's regulatory capacity by using land to feed people. This is why climate scientists, and I am so concerned that we have already set in motion perhaps irreversible climate change. Now, global heating 55 million years ago had some differences. It took place much more slowly than now. The injection of the carbon compounds took place over a period of about 10,000 years instead of 200 as we're doing. And in his paper, Professor Elderfield suggests that because of the slow rate of introduction, CO2 rose to no more than 440 parts per million at the maximum. And that's only a little more than there is in the air now. You see, I think it's about 383 parts per million, but in addition we have other greenhouse gases, methane, nitrous oxide, CFCs, that bring up the total effective to about 420 to 430, very close on 450. The great rapidity with which we add carbon gases to the air is as damaging in some ways as is the quantity. The rapidity of the pollution that we're doing gives the Earth system little time to adjust, and this is particularly important for the ocean ecosystems. The rapid accumulation of CO2 in the surface waters is making them too acid for shell-forming organisms, and that includes a small algae called the coccolithophore, which is vital for the CO2 cycle. It forms shells that settle and so take carbon dioxide from the top ocean surface and from the atmosphere. Now, this kind of acidity didn't happen in the Eocene event because there was time for the more alkaline deep waters to mix in and neutralize the surface ocean. There are other differences between the Earth 55 million years ago and now. It was about 3 degrees warmer at the start of the event, and it took place on an Earth with a more uniform temperature than now. That was because there was no Antarctic continent, and therefore no polar ice caps. On the other hand, as I mentioned, the sun was 0.5% cooler, and there was no agriculture anywhere. Natural vegetation was free to regulate the climate. Another difference was that the world, and this is an important one, was not then experiencing what we in the climate community call global dimming. This is a 2 to 3 degrees of global cooling, particularly over America and Europe and China, caused by man-made pollution. It's an aerosol haze in the atmosphere that reflects sunlight back to space. But more important, it's also an aerosol that nucleates the kind of clouds that reflect even more sunlight back to space. The particles of this haze persist in the air for only a few weeks, and whereas carbon dioxide, of course, persists for very long periods, well over 100 years. So any economic downturn or a plan to cut back in fossil fuel use, as recommended in Kyoto, which lessened this aerosol density, would immediately intensify heating. And this is why I think we live in a fool's climate. We're damned if we continue to burn fuel, and perhaps damned if we stop too suddenly. Now, in saying these rather awful things, I think it's important to note that I'm merely the messenger who brings the bad news. And you will ask, what should we do? Well, my only certainties are that the Earth system, Gaia, will survive, and so will humans, because we are a very tough species. And the record from that event 55 million years ago shows that there was no great extinction. Life continued. It had to migrate to the poles, and when things cooled down again, to move back. And you might think about it, because the polar ocean at 55 million years ago was 23 degrees Celsius, and crocodiles were living in it. Their remains are found in the fossil record. Now, in no way do I think there's no hope for us, or that there's nothing we can do. I see our predicament as rather like that we faced in the United Kingdom in 1940, when we were about to be invaded by a powerful enemy. But now we're at war with the Earth and faced with a hell of a lot more than the blitzkrieg. We have to do our best to cut emissions and lessen our destruction of natural forests to feed and house ourselves, but equally we have to learn to adapt to the ineluctable changes we may soon experience. And among the remedies we have to consider is mitigation of global heating by sunshades. Yes, there are people at Lawrence Livermore who already have plans for carbon fiber sunshades at the Lagrange point in between the Earth and the Sun, which they say would not be different in cost appreciably from the space station. So it's not to be sneezed at. And I know environmentalists would immediately say that's a mere technological fix, no good. But if it buys us time, then we should consider it. A more seriously suitable mitigation would be merely to get the airlines to burn sulfur-rich fuel and pollute the stratosphere and so cause sunlight to be reflected back to space. This happens every time there's a big volcano, and we know from past experience that big volcanoes like Pinatubo cooled off the Earth for about 5 years. So it's not entirely impractical, and as I say, we should consider it. But you do have to keep in mind the environmentalists are right. In the longer run, they're no more of a cure than would be dialysis for kidney failure if any of us got it. But then who would refuse dialysis if death was the alternative? Perhaps the saddest thing about this story is that if we fail, Gaia's going to lose as much or more than we do. Not only will wildlife and whole ecosystems go extinct, but in human civilization, the planet has a truly precious resource. We're not merely a disease, we are, through our intelligence and communications, the planetary equivalent of a nervous system. We have to keep that in mind because we're as much part of it as any other living thing. And we should be the heart and mind of the Earth, not a malady. I've tried to show that my theory reconciles current thinking in evolutionary biology with that in evolutionary geology. It extends, not contradicts Darwin's vision. The theory is, of course, provisional, but it provides an intellectual habitat where understanding of the Earth can evolve and grow, something that we badly need. Perhaps its greatest value lies in its metaphor of a living Earth, which reminds us that we are part of it and that our contract with the Earth is not only about human rights, it is about human obligations. Thank you. Okay. Thank you, Armando.
What we'd like to do at this juncture is to open up for questions, and we do have a few question leaders that we've asked, like Dan Fernandez, the president of our faculty, Tristan, the environmental scientist here, Tim. We'd like you to step forward to the mic here. We'll take questions for several minutes, and then we would like to have a critical examiner in our Professor Amalia Mesa-Baines. Dan Fernandez, the president of our faculty senate. Yes. Let's see if it's on. You want to test that?
Yeah.
This on? Yeah.
A little more.
Okay, I'll try to think of something intelligent to ask here. One question I had is it's on a detail. Did you give the rationale for why the temperature drop was rather smaller? I can see why the CO2 dropped, because I assume because of the loss of life of algae.
No, the CO2 drop at the end on the black line was a kind of model thing. We just said, introduced into the model the fact that the CO2 is now back to where it was, to see what would happen. It was an experiment.
Okay. But that didn't result in a significant temperature drop?
No, it didn't.
What was the rationale for that?
Oh, well, I think you can see the world was then being regulated only by the plants on the land, not by the algae in the ocean, and the response of the system was to just leave the temperature where it was. There was no...
And my other more general question is, are there any other significant factors that you're not really taking into account here? You have the CO2, you have the temperature, you have the plant life. Are there any other...
Oh, you're so right. It's an exceedingly elementary model, but not meant to be more than an illustration of the general picture of what's happening. It needs to be made into a two-dimensional energy balance model of the climatologist kind, and lots of other things need putting into it. But it's important in that it's quite different from even the big IPCC models. They just show temperature going up and up and up and up, and if you continue putting in CO2, it just runs off the screen. They don't show any stable state emerging at a higher temperature, and I think this is important.
Thank you.
Would you elaborate on the impact that burning sulfur-rich fuels by the airlines would have? How much of a break would it give us, and what would some of the negative effects of that be?
Well, the idea was first suggested by the Russian scientist Bodaiko in the 1970s, and it was thrown out by most of the climate community on the grounds not that it wouldn't work, but that it would encourage people to go on burning fuel. It was examined scientifically by Dr. Robert Dickinson, who's a scientist in Arizona. I'm not quite sure what university he's at, but he's a very highly respected climate scientist. And if you're interested, he had a paper in the 1980s, I think it was, or 90s, in the Review of Geophysics that is really authoritative on the whole of this issue and discusses almost all the points you would be interested in. It really works in the same way as a volcano. It's not much of a damage to the stratosphere any more than Pinatubo was. It may slightly affect ozone depletion. I'm not sure even which way, whether to help it or to lessen it, but whatever, it's not a large effect. And but the problem is, of course, we go on doing what we're doing.
Do you reference this in your book?
Which?
Did you reference the
Dr.
the application
Dickinson's
of
paper?
The sulfur-enhanced fuels in
No,
prevention
not I mentioned it, but no more than in passing.
I'm David Loy with the General Evolution Research Group, and I met you years ago in Florence.
Oh,
And I
that's
corresponded
right, yes.
recently, and I want to thank you for your permission to use that eloquent essay in my new book, The Global Sounding. I have the galleys here, and I wonder if I could catch a minute with you after you do the autographing.
Certainly.
No more commercials.
Only a minute.
Okay,
Carry on.
okay.
Hi, Mr. Lovelock. My name's Tristan. I am the environmental senator for this university. I like to think of myself as the student representative as far as environmental concerns go.
Good.
First of all, I'd just like to say that when I read your book, I actually was backpacking in the Trinity Alps, which is quite refreshing to be in one of the most pristine areas in California and,
Yeah.
reading about these kind of things. And as kind of an interesting note, I was actually, there were forest fires going on in the Trinity Alps during the time I was there, and they were actually just a couple ridges over from myself. So the entire time we were there, we could actually see all the smoke, and during the nighttime, all the smoke would come in and just kind of cover our campsite. And I was sitting and reading your book, and I came to a passage that was about how the Earth kind of regulates itself, and all of a sudden I looked up in the sky, and clouds just started moving. They were collecting, they were just congregating in the sky and just moving directly to the fire. And a couple days later, it started raining, and the fire started being contained by itself. And it was kind of ironic because there had been firefighters the entire time, collecting water from the lake, thinking that, they had the control over the fire.
I think you are probably seeing the more normal response of the system to forest fire. Sadly, if you go a good bit further north into Canada or Siberia, that sort of regulatory response is no longer happening. I think in Siberia they lost an area the size of Italy to forest fires last year, and there's every sign that this year is going to be as bad.
So I guess my question would be, because as a student representative, I would hate for at least all the students in here to leave thinking that we're waiting for the airline companies to do something about it, or we're waiting for the people who control the, you speak about nuclear power as a very immediate solution to the problem, but that doesn't quite involve us as individuals who are sitting in this room. And so I'd really like to get your take on what can we do as, as individuals who are probably going to be home tonight. We have to make dinner first. I mean, we have our survival priorities first. We have family. So what are things that, we can fit into our general lifestyle without making like immediate shocking changes, like saying like, all right, well, I'm just going to drop out of school so I can just try and solve global warming. Like, what are some? Because I just want to, what are some?
Thank you for that. That you couldn't have put it better. As I said, I'm just the messenger. Right. It's not really my job to plan the lives of you all way ahead. I won't see any of it. And that doesn't make me laid back about it. I have 9 grandchildren, so I am concerned. It's very difficult to make recommendations. You're absolutely right. People will try and fix it with things like the stratospheric aerosol or the sunshades or even other things, but it isn't really the answer at all. And an awful lot is going to come onto your generation for doing things, which might in the end, the worst scenario is migration northwards. I think the most important things to keep in mind is that the Earth is a self-regulating system, and because to understand it and stop in the future doing bad things, we need to know that, and also to take comfort from the fact that the evidence suggests that the system is exceedingly robust and has survived far worse insults than what we're doing, or that event 55 million years ago. And also that humans are a darn tough species, so we're going to survive through it.
So do you think there's enough room at the North Pole for how many people? 6.8 billion?
Well, that's for you. It won't be the North Pole, it'll be North Canada.
Right.
Right.
Thank you.
You're welcome.
Thank you for coming today, Dr. Lovelock. My name is Tim Gallardo. I'm just coming down from UC Santa Cruz with a bunch of students as well, and taking that same perspective as Tristan in terms of what we work into our lives to look towards a sustainable future. But if what you're suggesting is that, in fact, we will go through some intense heating periods where the polar sources, geographic spaces, will be our only viable spaces for continuing human populations, I think that's a big thought to think about. And I think a big thought for youth to think about and to put into our landscape today. And I guess my question for you is realizing that, we've overloaded our carrying capacity for the planet, it seems, with human populations, and it seems it's not going to diminish in terms of just from our own abstinence or advice in our cultures themselves. We've also diminished the resources of this planet, learning what we've done with industrial civilization and post-industrial civilization and placing that model in developing nations. What should we take with us to the polar ice caps, and what should we certainly leave behind? I mean, we've learned a lot from civilization, but is civilization itself sustainable? And if not, should we move back to simplistic relationships? Or are we moving forward with technological advances and fixes that we want to carry forward into the next, remodulation of human societies?
There's a lot of good questions there. Hang on. Well, I think towards the end of my book, I mention the possibility of a book that will be in every home that would contain the hard-won facts of our civilization, which are not by no means all science facts. They go right across the board, including personal behavior, being decent and all the rest of it. But one of the obvious hard-won facts to illustrate what I'm getting at is the fact that infectious disease is caused by bacteria and viruses, tiny things too small to see, and not by some witch who lives in the woods up there or by some angry god up in the sky. That kind of thing could save an awful lot of time and trouble for future civilizations if they are unfortunate enough to go through a dark age before they get their act together.
So we should leave our televisions and cell phones and everything behind for the time.
Well, I hope they'll take cell phones with them. They're one of the most green inventions there ever were, and an example of how technology can be good as well as bad. I mean, dash it all, few things have saved so much energy use than cell phones. Think of the time people waste on them that they might otherwise be driving around or burning trash or something.
Thank you.
Dr. Lovelock, and welcome to CSUMB. I'm a new faculty member in the social and behavioral sciences and history, so I'm not a scientist. And my question, I think, is a little bit different. As I read your work and as I listened to you talk, it was very familiar to me, and I knew why. It's because I grew up with it, not in scientific terminology, but rather through what my elders taught me. And throughout indigenous communities, our elders teach us that you take what you need, you use all what you take, and you always, always, always respect the source. And the source is the earth, and that we are part of that earth. And I was wondering, this is such a deep philosophical, spiritual, and now you've confirmed my belief, scientific belief system. Have you had any dialogues with indigenous communities or indigenous scientists about what we can do to work together about that? Because it seems to me that the indigenous population of the Americas have been kind of pushed aside. And do you have any thoughts about that?
I have. I thought about it quite a lot, but the spiritual side of it, because I'm an agnostic, and would rather not get. The situation is complicated enough as it is, without bringing in that dimension as well. It's also a very fraught and battling one at the moment. But I do hear what you're saying, and I think there are stages in the development of human society. I mean, first of all, we were hunter-gatherers, and then we became farmers. And the elders you're talking about probably come from one or other of those groupings. In North America, they certainly did do farming, but they also did hunting and gathering. And they were perhaps a lot more at equilibrium with the earth than we are now, but they were still doing a few bad things like fire drive hunting and so on. And in certain ways, our fall from grace was when we started using fire, which was the very first act of technology. And it goes back an awful long way, probably 100,000 years. There's good evidence now that the first people that moved into Australia 100,000 years or 50,000 years ago wiped out the ecosystems of that planet in amazingly short order, almost as good as agribusiness farmers. So I think we're all bad. There's no goodies anywhere.
Well, I'm not that old. My elders that taught me weren't that old either, but because they were, I do come from a farming community. But what kind of answers do you think we could come to together in terms, regardless of the spiritual? I realize that is often a contentious area, but I mean, indigenous scholars and scientists are really working toward solutions in terms of how we deal with the ecosystem. And I was just wondering if you've had any communication with them about what they're doing within their own communities.
I haven't, but I think those that have got to live ahead through the future, as the young environmental representatives said they should.
Okay. Thank you very much.
Thank you.
Thank you, Dr. Lovelock, for being here and doing your talks. My question to you is about the use of nuclear power energy. And in an article that was announcing your arrival here to give this talk, it says that you endorse nuclear power as a solution to global warming. And I didn't hear your entire talk, so I don't know if you've already talked about that, but if you could talk about that, and also for someone, something that I'm struggling with is I think in terms of technological advances, and then how human lifestyles could change, and I'm wondering which approach is more reliable to even hope that that we could hope for the best for the future.
If I got you right, you're asking me about nuclear power?
Yes, and the technological, that's a technology, that as an advance in technology.
Right.
Versus hoping that people will change their lifestyles, like stopping to drive as much and flying.
It's a complex issue. I'm not a wildly fanatical supporter of nuclear power, but I think for certain countries and certain places, for example, where I live in the UK and Western Germany and parts of Europe, nuclear power is almost essential. if they're going to run their civilization. In America, you've got bags of room for solar energy, for renewables like wind energy even. We don't. And the sunlight doesn't shine as comfortably at latitude 52 north as it does here. So solar is not very good. And that leaves us nothing really that's totally reliable but nuclear. I mean, take the UK, for example. In 15 years, our only source of energy, if we don't sustain nuclear power, will be Russian gas. Now, coming along a single pipeline. Now, that, I don't think, is a very good source of energy to rely on for everything. You see, any major city, big city like London, New York, San Francisco, Los Angeles, anywhere, if you cut off electricity for just 1 week altogether, it will die. It'll become like one of those camps in Darfur. It'll be that bad because everything stops. Spend some time thinking about all the things that would stop if electricity stopped. And you realize how essential it is. Now, there's no more reliable source of electricity that just keeps going and doesn't depend on supplies from abroad than nuclear. So that's why I advocate it. I think its dangers, even if I agreed with people that it was dangerous, and I don't, I think they've been vastly exaggerated because we were, and rightly in a way, because during the Cold War there was such a risk of all-out nuclear war that you had to exaggerate a bit to make sure people fought against it. But now in these times, nuclear energy is a benefice, a boon that could help us in our struggles, not a curse.
So would you say that technology is advancing enough to be able to address nuclear fallouts and the disposal of nuclear waste? Is there hope that we can improve those dangers?
As an example of the exaggerations and nonsense, I had dinner with Hans Blix, who you've no doubt all heard of, a couple of years ago, and he said, I cannot understand why there's all this fuss about nuclear waste. There's hardly any of it, is there? And when you look at the total quantity of high-level waste, that's the only one that's dangerous. It's tiny, so small you could almost forget it. And it won't hurt anybody. It's fused lumps of glass made up as bricks. If you go and sit on it, of course, it'll kill you, but why do it? Whereas every year that passes, the carbon dioxide waste that will kill most of us, regardless, if you froze it, would make a mountain 1 mile high and 12 miles at the circumference. Just think of it. And every year that mountain is added to and gets bigger. Compared with nuclear waste, by comparison, is a trivial, unimportant problem.
Thank you.
Thank you, Dr. Lovelock. If given during the last episode of global heating, the end of the last ice age, produced in our species the response of agriculture and eventually urban civilization in the world we know, I wonder if in your writing and thinking, if you've given some thought to some scenarios, given the maps that you have shown us, about how these sorts of changes might evolve, various kinds of either migration scenarios and other methods or pathways of transformation. Thank you.
I didn't quite hear that clearly. Not your fault. I think it's the sound system at this point. Are you asking me if I have any scenarios for migration or what?
Oh, scenarios that have occurred to you while thinking about, as the world heats up, the kinds of transformations analogous to those that happened the last time.
Yes, I've thought about it a lot. Give you an example of how serious it is. Several of the prominent scientists involved with the IPCC report have pointed out, and this is a thing which isn't in their report but comes from it, that by somewhere between 2040 and 2060, if you take Europe, for example, the summers every year would be as hot as the summer in 2003, when between 20 and 30 people died of heat stroke. You might say, well, if it gets that hot, they can turn up the air conditioning or something, if they've got the energy to do it with, yes. But that's not the point. The point is that sustained summers of that heat make agriculture almost impossible, and Europe would revert to scrub and desert. And it would be, what are the 400 million people who live in Europe going to do? Well, they can migrate to the British Isles. They have complete right to do so. But I'm afraid it's going to be standing room only where I live. That's the wrong migration. But it is coming up on us fast, and we've got to think about it.
Thank you.
Oh, did I? Yeah. Oh, never mind.
Hi. From listening now and from following your earlier work, the question comes like, where would we be without you? You've done this your whole life, and up till now, what finally draws you to it or keeps you in it? Just the pure research, or trying to find hope, or to warn people, or something that I can't guess at? Like, why are you still in it? Where does your intensity come from?
Maybe because I'm a passionate person by nature, and it seemed important to me that the theory was established finally, I mean, for purely selfish reasons, for the sake of recognition. Also, a growing awareness of how bad it was. I mean, this drives you to speak out as I've done. All our motivations are horribly complex, and one can go back, some good, some bad motivations. If you give me your email address, I'm good to send you it when I've had time to think.
Hello, I just have a quick question. And one of the arguments against global warming as a cause by greenhouse gases is the fact that the solar system is also warming. And I guess they have data that shows that other planets are also showing increases in temperature globally. And so I was just wondering how you looked at that, just kind of a quick reflection.
Yeah, if I get you right, you're asking how good is the evidence that global warming is caused by greenhouse gases, and how have we rejected the evidence that the solar energy output has changed? Is that right?
Right, because it is kind of coincidental that the whole solar system is also increasing in temperature. And I mean, there is proof that the greenhouse gases increase temperature, but what I'm wondering is how the course of our solar system as a system in general influences your Gaia concept, which is the fact that our Earth is an organism and a system that self-regulates as well.
All I can say really is that the evidence as presented in, for example, the IPCC report is exceedingly thorough and takes account of solar energy change, solar output change, as well as greenhouse gas accumulation, and allows for lots of things. Admittedly, they don't include everything, and it's their hope and my hope that the models will grow ever more detailed as information and understanding grow. But at the moment, they're pretty good. I think we would be most unwise and irresponsible to ignore what they suggest.
Thank you.
What we're going to do is to give you a short break.
Thank you.
I've got one more.
No, we're done. I'm sorry. Sorry. We do have to draw the line somewhere. And this is being edited by 3 different TV cameras, by the way. But thank you. What we would like to do is to give you a short break.
Thank you.
And just a short one. And we're asking Dr. Amalia Mesa-Baines to give us a summative analysis and also a critical examination, because that's what we do here. That's one of our core values in our vision statement, as a matter of fact. So we would like to take a few minutes and ask Dr. Baines to help us with those ideas, and then follow up with a closing presentation and a book signing, and then it's time to rest.
Thank you, Armando.
We've asked Dr. Amalia Mesa-Baines to provide us with a short summative analysis as well as a critical examination of Dr. Lovelock's lecture. You may be interested to know that Dr. Mesa-Baines is an artist, cultural critic, and a psychologist. Her works have been exhibited in both national and international venues, and Dr. Mesa-Baines holds a doctorate in psychology from Wright University in Berkeley. She's also the recipient of numerous awards, to include Distinguished MacArthur Fellowship, also known as the Genius Award. Currently, she is the director of the Visual and Public Art Institute here at CSU Monterey Bay. Dr. Baines, welcome, and thank you for taking this on.
I have to say, when I agreed to this, I did not recognize fully the depth of this role that I would take on, and I feel overwhelmed by the thought that I would have to speak after such an important message from such an eminent messenger. I had the opportunity also to hear Dr. Lovelock over the weekend at the Environmental Institute in Big Sur, so I've been pondering it for a while. I think it's very valuable that it happened here at CSUMB. We are a university that has been committed from our inception to interdisciplinarity, to the idea of environmental responsibility, to issues of humanism, justice, and diversity. And our own environmental science and policy program here has in some way evolved from the very foundations of thinking that Dr. Lovelock so beautifully presented today. But it's a message, a beautiful message with a painful center to it. And I think it's something that we reflect on, both as people in the mid-years of our life, for our students in the early adulthood, and for those of us who are older in life. Because each of us on this pathway must look at that future that he depicts today. And that future has with it potentialities that are frightening and terrifying to think about. But at the same time, each of us has this moment in our time and life to make choices and decisions that may in some way diminish, who knows, perhaps alter. I am always hopeful. But nonetheless, I took to heart the message that Dr. Lovelock brought to us, but I thought some of the most pertinent things had to do with the mistakes that were made in the past, and one of them was the concept of detachment, that the scientists who could not see this or act upon it or prepare us in a fundamental way, because both their detachment and perhaps their specificity. So once again, we look at our attachment to the earth. We look at our willingness to cross different boundaries in learning and intellectual, social, and cultural pursuits to try on some level to prepare ourselves for the future that he describes. His holistic model of a self-regulating body or body of earth, despite the fact that Dr. Lovelock describes himself as an agnostic, and religion is certainly not part of his makeup. For those of us who hold some spiritual sense of our relationship to the earth, perhaps then the role he casts us in this self-regulating system, we the humans as the heart and mind, the nervous system of this self-regulating body, need to think about what that means for us, both on the macro level of decisions that can be made in everything from the sulfur emissions of airlines to the tiniest gestures we make when we buy organic or recycle. Each one of us has to believe and hope that some gesture that we make repetitively in the years ahead will help us to prepare for this. And when he talked about the fact that we were the heart and mind of this body, this nervous system, I thought of our worldwide disruptions, our wars, our inhumanity to one another, and how much those decisions made in the midst of wars and moments of conflict have disabled us from thinking In the model that Dr. Lovelock presents to us, it is a model of survival. It's not a model about curing or saving, but surviving. And so when we think about that future life, what knowledge must we have to survive? What knowledge must we preserve for those who will survive when we do not? What is it that we imagine in the future to live in another place? The migratory concepts that he talks about of life in the Arctic makes us think about what our roles are now in preparing those of us who are younger, the children being born now, his 9 grandchildren, whoever they might be. How will they live in those other places if we are unable to stop the global warming that occurs? And so I think we do have a role, whether we are thinkers, scientists, artists, writers. We have a role to think about, teachers, educators, in which we can prepare those who come ahead. Walter Benjamin, a philosopher and scholar, once said, the dead have a debt with us that can never be settled cheaply. What he meant was, they who lived before us knew we were coming, and we owe them something. Well, the same may be true of us for those who come after us. We need to protect and preserve whatever part of life that we can. And I like his way of talking about us as a species that has the tenacity to survive. And I guess I would say in the end that the books that we read, the days in which we sit and listen to these lectures are just the beginning of mindfulness and purpose in our lives. I like very much the idea that Earth has its goal, and the self-regulating goal should be part of the goal that we have. And despite the fact that we may seem unprepared for the message, I think CSUMB is just the place for such a message to take hold, because I believe that it is the young people here in the environment of interdisciplinary learning who have taken that human responsibility that he talks about and moved it forward. And we, as their teachers and those who support them, their families, know that it's our investment in their future now. We must teach and learn and move toward that 7th generation, whether that 7th generation lives in the Arctic Pole or survives in a desert in the United States. It is our responsibility. We are the heart, the mind, and the nervous system of this whole body we call the Earth. Thank you.
Helping our planet and saving our Earth.
Thank you, Dr. Lovelock, for helping us and educating us about our living planet. And yeah, thanks.
Thank you very much.
Please join me in thanking Dr. Lovelock. We're now going to retreat to the lobby for a book signing. Thank you very, very much for coming today. All right.
Yes, thank you so much.